In this video we are going to learn sound chapter, which is a class 9th NCERT, chapter 12. So this is a very simple topic in which we will study how the sound propagates and how this propagation can be used in different way. Its application of sounds. So the most fundamental thing is how the sound is produced and how the sound travels in a medium. So production of sound, we just discussed about the propagation of sound, how sound propagates. Sound is produced by vibrating objects. It is produced by vibrating object. The matter or substance through which the sound is transmitted is called medium. So the sound is propagating because of vibrating objects, and the medium in which the object vibrates, it's called a medium. It can be a medium, can be solid, liquid, or gas. In all three mediums sound propagates. And here we can learn, in vacuum, since there are no objects to vibrate, so no medium is there. It cannot be medium can be only solid, liquid, gas, because these have objects, particles. So as vacuum has no objects, then no particle will be there to vibrate, and there cannot be any propagation of sound in it. So sound cannot travel in vacuum. Particles do not travel from all way from the vibrating object to the near ear. A particle of a medium in contact with a vibrating the particle of the medium in contact with vibrating object is first displaced from its equilibrium position. Then it exerts a force on an adjacent particle, as a result of which the adjacent particle gets displaced from its position to rest. After displacing the adjacent particle, the first particle comes back to the original position, and this process continues. This is how the sound travels. Let me give you an illustration. So this is how it, like, if like force, this is source of sounds, they vibrate, and this particle will push this layer of particles, and then again will come into initial position, and these particle will again push and vibrate a next layer of particles, and this one again come into at this original place, and the third layer will again push to the fourth layer, and this process continues. And this is how our human uh, this is how the vibrating particles reaches at the human drum. There is a eardrum in our inside our ear, and these vibrating particles reaches in human eardrum, and the eardrum also get vibrate. And we will study later what happens to the sound after hitting the eardrum. So there is experiment what can sound make a light spot dance. This is what the experiment, it making sound, and this is a mirror, and it's definitely when the layers of the particle in the medium will vibrate, obviously this rubber band, this glass will also vibrate. This glass will vibrate, it will like reflect the light slightly up and down. So this is how the like light spot can dance. Sound waves are characterized by the motion of the particles in a medium and are called mechanical waves. These are called mechanical waves because there is a mechanical movement is there. A region of a high pressure is called compression, and the region of the low pressure is called rarefaction. What is a compression and rarefaction? When the particles are very close in the propagation of sound, this is called compression, very close. And when the particles are very far, this is called rarefaction. There is example of it. uh, See, this was vibrated, this was hit by a hammer very hard, it vibrate. And this forms the vibration forms uh, the medium like this. And there is a high uh, high density particles, and there is a low density particles. So region of high pressure is called compression, this is compression. And region of low pressure is called rarefaction, creating a series of compression and rarefaction. And vibrating objects, creating a vibrating object create a region of rarefaction and compression. And sound needs a medium to travel, it needs medium, it cannot travel in vacuum because there is no particle to vibrate in the vacuum. uh, Bells are experiments showing sound cannot travel in a vacuum. This was the experiment was done. This vacuum was created, and when the ball is thrown here, it does not produce a hitting sound. No medium is there, no particles are there, so it sound cannot travel. Because to travel sound, how sound travels? It travels through vibrating particles. So there are no particles; they cannot be vibration. Sound waves are longitudinal waves. What are longitudinal waves? Those who propagates towards the direction of travel. Longitudinal waves. So this is in these waves. In these waves, the individual particles of a medium moves in the direction parallel to the direction of propagation. So the direction of the see, if the sound wave is going this way and direction of propagation is also this way, and this is called longitudinal waves. Here here its sound is going this way, this is the direction of propagation, sound is propagating this way. And also the waves, rarefaction and compression are the sound waves, these are called sound waves. And they compression, then rarefaction, then compression. And these waves are also in the direction of propagation, like if the sound is going in the east, the particles will also, are also vibrating in the east direction, in this way. So this is called longitudinal propagation of waves. There is another type of waves which is called transverse wave. In transverse waves, the particle do not oscillate along the direction of the propagation, but it oscillates up and down about their mean position of the wave travel. So transverse wave, like electromagnetic wave is an example of transverse wave. If this is the propagation, the wave travels this way, like it travels uh, transverse means it creates an angle 90, like opposite side this way. Is it not in the in the opposite, in the not in the direction of the propagation? Transfer wave particles do not oscillate along the direction of the propagation. They are not oscillating along the direction. Electromagnetic waves are which will we study in 10th class are transverse waves. This is a very good example of the longitudinal waves. And there is a spring, we are compressing it, the compression rarefaction is forming. And and this is also in the direction, this is how the longitudinal wave travels. And there are some characteristics of the sounds, which is frequency, amplitude and speed. Let's discuss this. So this is a sound wave. It looks speak there is a speaker and these are particles, and when it is vibrating, it creating this rear friction compression. This is compression and rear friction. And the compression, the between, we just draw a line. It will be the tuff, which is the peak point, and in the middle of the rear friction, it is the wave is going downward. This is a crest and this is a trough, and this, and from one, this is a wavelength lambda, from one dense compression to another compression, this is a lambda, and from one rear friction to another rear friction, this will be again lambda. So this is how this is the wavelength. The distance between two consecutive compression or two consecutive rear friction is called wavelength. This is lambda, a Greek letter lambda, and SI unit is meter. Hertz was born, is a scientist, was born in Germany, educated in Berlin, and confirmed the J.C. Maxwell electromagnetic theory by his experiment, and developed the radio, telephone, telegraph, and even the television. Also discovered the photoelectric effect and later explained by the Albert Einstein. Okay, frequency is now discuss about the frequency. Frequency tells us how frequent an event occurs, how fast an event is occurring, how frequent is event is occurring. So it is represented by mu, and it has a unit hertz. This is called nu or mu. This is like V like structure. It no V like, it is something like is this way. And frequency and time is like, if time increases, frequency decreases. If frequency increases, time decreases. Inversely proportional are they. The higher the frequency, the higher will be the pitch. So another concept, if a sound which has higher frequency, that means it has it what is frequency? Frequency is like uh, number of wavelength per unit time. Number of wavelength per unit time. This is these are two medium. Suppose in 1 second, wavelength are 1 2 3 4. There are six wavelengths. Six wavelengths per second, and in another propagation, there are only 1 second. Only there are two wavelengths. Two wavelength in 1 second. So frequency is more in it, because frequency of wavelengths are more in it, the frequency will be high. So higher will be the frequency, higher will be the pitch. And in this case, in case of sound, if the higher is the frequency, higher will be the pitch of the sound, and low is the frequency, low is and low will be the sound pitch. This is same explained here. Wave shapes the low pitch of sound, and wave shapes the high pitch of sound. Consider this time is a 1 unit. Suppose it is a 1 second time, and this is again 1 second time. This is how you will understand this. Low pitch sound has a low frequency, and high pitch sound has a high frequency. Loudness or softness of the sound is determined by basically by amplitude. How loud sound is, how slow, and how soft the sound is. It's about the volume. When we increase the volume, and what happens, the amplitude of the sound increases. Amplitude is the distance, the maximum distance from the mean to the crest or tuff. This is called amplitude. And when we slow down the volume of our mobile, the amplitude decreases, and vice versa. In when amplitude increases, the loudness increases. A sound of a single frequency is called tone. Sound which produces a mixture of several frequencies is called a note, and which is called musical notes. It is used in music and is pleasant to listen. So this is why the music is pleasurable, because it has the mixture of several frequencies. The speed of the sound can be found by wavelength divided by time. The wavelength, how what is a single wavelength? uh, this wavelength divided by time is called speed. So speed has a different sound has a different speed in medium. The speed of the sound decreases when we go from solid to gas. It decreases from solid to gas. In any medium, when we increase temperature, the speed of the sound is also increases. So for solid, liquid, gas, the sound decreases. The speed of the sound decreases the sound. And if we increase the temperature of any medium, the speed increases. And the in normal air means at like 0 degree celsius in air, the sound speed is 331, and 344 is at 22 degree celsius in a sound, in a sound, in a ear. This is it has shown the speed of sound in different medium. It is most in solids, then in liquids, and the minimum is in gases. Aluminum has aluminum, nickel, these are the metals in the sound travels too fast. In water and in waters and ethanol and methanol, the sound travels with this speed, and gas it is the slowest, and in air this is 442, and the sound we hear travels at this speed. What is a sonic boom? Sonic boom is like when the sound travels more than any object travels more than the speed of sound, then you know then a sonic booms happens. When the speed when the speed of any object exceed the speed of the sound, it is said to be a traveling a supersonic speed. The bullet, jet, craft, etc. often travels at a supersonic speed when the sound producing source moves with the higher speed than that of sound. It produces a shock wave in air, and these shock waves carry a large amount of energy, and the energy pressure variation associated with this type of shock wave pressure, a very sharp and loud sound, is called a sonic boom. Shock waves produced by the supersonic jetcraft have enough energy to shatter window glass and even damage the buildings. Now, what is a reflection of sound? The sound bounces off from the solid or liquid like a rubber bounces off a wall. Like light, sound reflected at the surface of a solid or a liquid and follows the same laws of reflection, which is the incident and the reflected ray makes the equal angle at normal. This is making equal angle. If it is theta, it is also theta. This is how the reflection of light the laws of reflection is light is also applicable in the reflection of sound also. What is an echo? The sensation of a sound persists in our brain about 0.1 second. So this long the sensation persists. To hear a distinct echo, to distinct voices, uh, the time travel between the original sound and the reflected sound must be uh, at least a gap of 0.1 seconds. If we hear a different types of sound zero in within the 0.1 second, we cannot differentiate the sounds. So just the different sounds can only be differentiated by our human brain when there is a distance of them from reaching to our human brain is 0.1 second. So just by calculating the speed of sound is this, and let's say in a year, so just multiplying it by 0.1 second, this thing comes, and this is like uh, there is an object. So 32, the sound must travel, must the sound must travel this much distance for echo. This is the total distance, so we will divide it by 2 because it will take equal distances while coming and going. So this is a ear, this is a sound source, and also the human ear, and there should be 7.2 should be the minimum distance. Sound go this way, it will reflect it from this surface and comes back, and there should be the minimum 17.2 meters of distance, and so that 0.1 seconds of difference can be created. If this difference is more or equal to this number, we will hear a different sound. So so um, we we heard an echo. This will be the echo in this case. And what happens, and what is reverberation? Reverberation is something else. The sound created by a big hole will persist by repeated reflection from the walls until it is reduced to value where there is no longer, or which is no longer audible. So this is what happens in empty hall. When we speak in an empty room, an empty hall, like our sounds, like our sound waves get multiple and repeated reflection till till the voice is no longer audible. The repeated reflection that results in this persistent sound is called reverberation. Okay, uses of, now let's talk about sound. Uses of multiple reflection of sound. Megaphones or like megaphones or loud hailer, horn, a musical instrument designed send sounds in a particular direction without spreading in all direction. So they are designed to send a sound in a particular direction. So sound travels more in this case. Stethoscopes. In stethoscope, the sound of the patient heartbeat reaches doctor by multiple reflection of sound. And this is how it travels. This is stethoscopes, and it travels like by multiple reflection. And cinema halls are generally covered by a sound observing seats, so that it's not a sound observing by generally ceiling. they are designed in this way. Matlab cinema halls are designed in this way, like sound goes this way, is it like it reflects in a way that it goes at the center where the people sits. Hearing range. Human hearing range is like the sound should have a frequency between 20 hertz to 20,000 hertz, 20 to 20k hertz. Children under the 5 or some animal such as dogs can hear up to 25k hertz. And below 20k hertz, this is called infra means is small and less superior. uh, Below 20 it is superior, is called infrasonic sounds. And rhinoceros communicate using the infrasonic sound below the zero point 0.5 hertz. So we cannot they communicate, so we cannot listen to the voice of rhinoceros because it communicates, we can only uh, hertz up to 20 hertz. Below this we cannot hear a sound, and rhinoceros communicates in 5 hertz. Earthquake produces low frequency infrasonic sounds before the main shock waves, which we uh, begins when a possibly alert, which possibly alert the animal frequency higher than. So this is see what happens in, we have some seen some movie, if earthquake was about to come, like most of animal changes their behavior, because before the earthquake produces low frequency infrasounds before a main shock wave begins, which possibly alerts the animal. So those animal might have ability to listen or feel low frequency sounds which humans don't have. That is why they get the early alert or indication of earthquake. Frequency higher than the 20k is called ultrasonic sounds. Ultra is more. Ultrasounds is produced by the animals such as dolphins, bat, and porpoises. Moths in a certain families have a very sensitive hearing equipment. These moths can hear a high frequency squeaks of a bat and know when the bat is flying nearby and able to escape capture. Moth is like butterfly, is a species of butterfly. Where is moth? Hmm. Butterfly. This is a similar like butterfly. Rat also play games by producing ultrasounds. Games is preying. In biology, the games mean preying on animals, preying on other animals. This is games. So rats also like prey on other animals by producing ultrasonic sounds. So the here is an example of the a butterfly. Butterfly also hears the ultrasonic sounds, high frequency sounds, and when the bird is flying, bird also is produces ultrasonic sound. Both of the species. When bird is flying, the butterfly can uh, sense it when it is flying nearby, and so that he can escape. Hearing aid. People with a hearing loss may need a hearing aid. A hearing aid is an electronic battery operated device. The hearing aid receives sound through a microphone, and microphone converts the sound into electrical signals. These electrical signals are amplified by amplifier, and amplified electrical signals are given to the speaker for hearing. So this is only amplifying the sound. This device only amplifying means it is the this altitude of the sound is increasing, altitude of the wavelength is amplified. Application of ultrasonic sound. It is used in cleaning parts located in hard reached areas like spiral tubes and odd shaped ports. Due to the high frequency, the particles of the dust, grease and dirt gets detached and drop out due to the high frequency. Also used in detect cracks and flaws in metal blocks, building like bridges, machines, and also in scientific equipment. This is used. And if there is a small defect, the ultrasound is reflected back. So this is a pictorial representation where when we are passing ultrasonic sound in a block, when it is where it is cracked, it is ultrasound is reflecting back from the crack. So these are the detectors, and these cannot as so here they it has not detected any uh, wave, since no wave is there. So this is how we can also identify the cracks. We are almost about to finish this chapter. uh, Ultrasonic waves also reflects the various parts from our heart and forms image of the heart. This is called echocardiography. Ultrasound scanner is an instrument which uses ultrasonic waves for getting image to the internal organs of the body. This is called ultrasonography. Like gallbladder, kidney, we do ultrasound. When even the pregnant women also do ultrasound, and a lot of when the patients having a various like stomach aches and stomach disease also do ultrasound to make a clear image, to getting a image of internal organs. Getting an image of internal organs, the ultrasound is used, and this way this technique is called ultrasonography. Ultrasonography is also used for examining the fetus during pregnancy to detect congenital defects and growth abnormalities. Ultrasound may also be employed to break stones formed in kidneys into fine gains. So kidney stones can be breaked. Uh, they are called like some calcium calculi. Kidney stones are calcium calculi. These are the calcium deposits, and when ultrasound is hit, they breaks down, and this is how it works. What is a sonar? Sonar is a full form. Sound navigation and ranging. It is used in measure the distance, direction, and speed underwater objects. Sonar consists of transmitter and a detector and is installed in a boat or a ship. So this is a boat, and here the sonar is placed. It what it does, it scans the underwater surface and detects any like hard rock and vegetation, all that, the distance between the sea bed to the boat. Ultrasound sounds sent by the transmitter and received by a detector. This is sent and this is received. The above mentioned is called echo ranging. The above method is called echo ranging, is used to determine the depth of the sea, which is a seabed, and also to locate the underwater hills, valleys, submarines, and icebergs and sunken ships. Shrunken ships. Shrunken ships. Like if ship is shrunken, so it just detects the distances. You know. As mentioned earlier, birds search out prey and fly in the dark night by emitting and detecting reflection of the ultraviolet sun. So the sonar is also based on the principle how the bat detects its prey. Sonar doing the same thing what bat is doing. Porcupines also use ultrasound for navigation and location for food and dark. This is a marine animal, like dolphin like animal. Porpoise. And let's go through the structure of human ear. You must have remember in the starting of the video, I tell you, like, the from the source the sound travels into multiple compression, rarefaction. The it keeps the vibrations is being sent to the next layer of the particles. So it reaches at human eardrum. What happens after that, we will discuss this. The outer layer is called pinnaca. This is pinna. Pinna. It collects the sound from the surrounding. It collects the sound. This part. The collected sound is passed through the auditory canal. This is the auditory canal. It is collected sound is passed through this, and at the end of the auditory canal there is a thin membrane called eardrum, and this is the eardrum. Uh, this is a eardrum, or this is called tympanic this tympanic membrane. This is called also tympanic membrane. When a compression of a medium reaches the eardrum, the pressure on the outside of the membrane increases and forces the eardrum inwards. When there is a compression, the sound travels in the compression and rarefaction way. So when the compression reaches the eardrum forces inwards. Similarly, eardrum moves outwards when the rarefaction wave reaches it. In this way, the eardrum vibrates. This These vibrations are amplified several times by three bones: the hammer, anvil, and stirrup in the middle ear. And there must be some hammer in middle ear. By three bones, this vibration is amplified. The middle ear transmits the amplified pressure vibration received from the sound waves to the inner ear. So the amplified sound goes to inner ear. What happens in inner ear? The pressure vibration are turned into electrical signals by a cochlea. This is called cochlea. So what is cochlea is doing? It is turning the pressure vibration into electrical signals. These electrical signals then sent to the brains via auditory nerves, and the brains interpret them as sounds. So these are like how the brain interprets sound is a very interesting concept. Like, there are different types of sounds. This different types of we interpret by it. There is a separate branch for it, like how we interpret a sound. So it will take a longer explanation for that. Let's leave it. So the brain interprets the sound. It interprets the sound waves, the electrically reached sound nerve through the sound auditory nerves. Electrical signals. Let's revise it quickly, go through it. The sound is produced due to vibration of an object. Sound wave travels as a longitudinal waves through the material medium. It cannot be in a vacuum. Sound travels through successive compression or rarefaction in the medium. In sound propagation, it is the energy of a sound that travels and not the particles of the medium. Only energy travels. Sound cannot travel in vacuum. The change in the density from one max value to a minimum value and again one max value makes one complete oscillation. And the distance between two consecutive compression or two consecutive rarefaction is called wavelength. And the time taken by a wave for one complete oscillation of a density or a pressure of a medium is called a time period, and the number of complete oscillation per unit time is called a frequency. Complete oscillation means this, it goes up and it goes down, and this is complete oscillation. There should be a complete cycle. This half circle is there and this half circle is there, and the circles completes, and this is called a complete oscillation. And the more is the complete oscillation per unit's time, more is the frequency, and vice versa. Speed mu speed v, frequency mu, wavelength lambda of the sound relates to the equation v equal to lambda speed equal to wavelength into frequency. Speed of sound depends primarily on the nature and temperature of transmitting objects. More the temperature, more will be the speed of sound. Nature means in solids the sound is highest, liquid says in medium, and gas it travels at the slowest speed. Laws of reflection of sound state that a direction in which the sound is incident and reflected makes the equal angle at normal. Same thing like reflection of light. The laws of reflection of light also works in the laws of reflection of sound. For hearing a distinct sound, a interval between the original sound and reflected sound must be 0.1 second. There should be a gap of this much time, so that our human brain can interpret the sound differently. The persistence of sound in an auditorium is a result of repeated reflection, and this is called reverberation, and this is what also happens in hall or empty room. The sound properties such as pitch, sound has sound properties such as pitch, loud, more frequency, if there is more frequency this is high pitch, and low frequency is low pitch. Loudness, its amplitude is more, it is a loud, its amplitude is low, it is softness. And quality are determined by the corresponding wave properties. Loudness is a physiological response to our ear to intensity of the sound. The amount of sound energy passing each second through a unit area is called intensity of the sound. Audible range of the human ear is 20 to 20 kilohertz. 20,000 hertz. 20 to 20,000 hertz. And below audible frequency is called infrasonic, and above the audible range is called ultrasonic. If sound is less than 20 hertz, it is infra, and if it is more than the 20,000 hertz, it is ultrasonic. Sonar is used in determining the depth of the sea, and bats also use this principle also. Bat. And to locate the underwater hill, this is used to locate underwater hill valleys, submarine, icebergs, and sunken ships. Thank you for watching this video.